This is experimental design question number 1 from Unit 1. A group of students has 2 carts, A and B, with wheels that turn with negligible friction. The carts travel along a horizontal track. Cart A has a known mass. The students are asked to use a one-dimensional collision between the carts to determine the mass of cart B. Before the collision, cart A travels to the right, and cart B is initially at rest, as shown in the diagram. After the collision, the carts stick together. So hopefully you're thinking conservation of momentum here. So part A says describe an experimental procedures to determine the velocities of the cart before and after the collision, including all of the additional equipment you would need. So I'm not going to tell you exactly how to do this because I want you guys to start practicing. But what you need in order to solve a conservation of momentum question, you need speeds and you need masses. Now, we know the mass of cart A and we're looking for the mass of cart B. So what we really need are the speeds. So what you need to solve this is you need the speed of cart A before the collision. And then since we're told that they stick together, you just need one more speed of A plus B after. Now, how you describe doing this is fine. You can say use a motion detector positioned, a certain place to find the initial speed of cart A. Then you'll need another motion detector to do A and B together. If you'd rather tape off like a meter with tape and do distances and times, you can do that as well. But those are really the 2 ways to go about that. So for the rubric, 1 point for a reasonable setup, 1 point for indicating all the needed measurements. So you need the speed of cart A before, and you need the speed of carts A and B together after. And then 1 point for nothing that's obviously not needed. So, if you said, I need to measure the acceleration of something, or I need to measure the force on something, then that would be wrong. So that's part A, 3 points. Sorry, I should have said I would also include in that procedure multiple trials to reduce error. Part B is a little tricky. It says there will be sources of error in the measurements taken in the experiment, both before and after the collision. For your experimental procedure, will the uncertainty in the calculated value of the mass of cart B be affected more by the error in the measurements taken before the collision or by those taken after the collision, or will it be equally affected by both sets? Of course, you have to justify your answer. So I went around this several times on my own and looking at the solution, and I think what they're saying here is, let's say you're using a motion detector, and let's say the margin of error is 10%. Well, the speed of cart A before the collision is going to be greater than the speed of cart A plus B after the collision, right? We know it's going to slow down without even putting any numbers in here. So I think what they want you to say is, let's say the equipment is accurate, so within 10%. Well, 10% of this number is going to be more than 10% of this number. So the answer is your uncertainty is going to be affected more by the error in this measurement because it's a bigger number. So 10% of a bigger number is going to be more than 10% of a smaller number. So the rubric there says 1 point for a reasonable assumption about the relative size of the measurements. Okay, so that's 1 point for saying, speed A is going to be bigger than speed A plus B. And then 1 point for saying, well, if it's accurate to within this percent, the possible error is going to be bigger for cart A. So that's 2 points for part B. If that part made no sense to you, that's okay. That's why we do these problems. It's going to come up and we're going to get more used to it. All right, for part C, we're actually going to determine the mass of cart B. And so we're looking at our velocity versus time graph, and the shaded circle is cart A and the dot is cart B. So you can tell by the graph that the carts collide at about t equals 1 second. Before that, cart A is moving at a reasonably constant speed, which I can tell from the slope of the graph. Cart B is at rest, as I can tell by the graph. So I use the slope of the line, and this is where I would honestly, if possible, print this out. And I printed it out and drew a line of best fit for both of these. It was very hard to do on the graph, and then just for kicks, I tried to pick a couple data points to see if I could calculate it. It was way off, and you're going to get dinged for that. So I know it's going to be hard because you're doing the test digitally, but I would still, where they have a graph like that, if you need to determine a line of best fit, I think it's worth your time to print it out. It's up to you. So I got a speed of cart A before the collision of about 1.5 or 1.6 meters per second, and then a slope of A plus B after the collision of about 0.6. So I substituted here my mass of cart A, my velocity of cart A. I guess you have to distribute this because this is your unknown, but it's just algebra. So the mass of your cart B is about 3/4 of a kilogram, right? Around 0.75. So again, you're going to be showing your work. What they're going to be looking for is the graphs here. So don't worry if your answer was a little bit off if you did the correction right, because here comes the rubric. 1 point for describing how to use conservation of momentum. So a point here. 1 point for realizing where on the graph is before the collision and where it is after. So hopefully I did that enough. 1 point from using the data from the graph to find the speed from the slope, because again, we have a position versus time graph. Slope is the speed. And then 1 point for using the slope of one or two lines to determine speeds. And they made a specific point of saying this point cannot be earned if you use data points that were not on the line. So for example, one of the data points for the before that's not on the line was my data point at 0.8 seconds and 1.2 meters. So you don't want to use points on the line to make or points that aren't on the line to make your best fit curve. So I hope that made a little bit of sense. Part D says the students are now asked to consider kinetic energy changes in an inelastic collision. Now I'm going to sidebar here. We know that we're losing energy here in the inelastic collisions because you know that from Unit 5. This says specifically whether the initial values of one of the physical quantities affect the fraction of mechanical energy dissipated in the collision. So basically, if I monkey with the initial velocity, or if I monkey with the mass of these objects, how does that change the percentage of kinetic energy dissipated or lost? Okay, so that's what they're saying. How could you modify the experiment to investigate this question? Be sure to explicitly describe the calculations you would make, specifying all equations, but you don't actually have to do the algebra. So I would start this off by saying to determine the percentage of kinetic energy dissipated, determine the kinetic energy of cart A before the collision, then determine the kinetic energy of cart A plus B after the collision, and compare those numbers. Then I would say, well, I would vary the mass of cart A and do the experiment again and see if the percentage changed. Then I'd vary the mass of cart B and see how the percentages changed. Then I'd vary the initial speed of cart A and see how the energy changed. Make sure in a part like this, you only change one thing, right? You're not going to say, oh, I'm going to change everything and see what happens. Well, we've got to establish cause and effect. So for me, that would be I would do this 3 different times. Once, keeping everything else the same, vary the mass of cart A. Then again, go back to initial conditions, vary the mass of cart B. Go back to initial conditions, vary the initial speed of the cart. That's all you can do. So be sure here that you indicate what you would calculate, but you don't have to actually do the calculations. I think I would indicate my formula for kinetic energy. I'd say I'd calculate the kinetic energy using this formula and maybe specifying which mass you were going to use and specify which velocity you were going to use, but you don't have to do the math. So that's part D. 1 point for describing a modification to vary the initial velocity or one of the cart's masses. 1 point for using the data to find initial kinetic energy and final kinetic energy. And then 1 point for indicating that the fraction of kinetic energy loss should be compared. Now, I think I said percentage when I was describing, but either one, right? The fraction that was lost or the percentage that was lost. Don't compare amounts. Don't say, oh, I lost 5 joules in this one and I lost 10 joules in this one, so it must be more. You can't do that. You've got to compare apples to apples. So that's either fractions or percentage. So that's number 1. Hopefully it made a little bit of sense to you.